Let's jump right in. Today's explainer is all about data structures and algorithms. But honestly, we're tossing out the traditional playbook. We're going to learn algorithms through pure logical deduction, completely stripping away that terrible need for rote memorization. We are building this from first principles, and we're going to do it together. So, have you ever solved a coding problem, felt absolutely amazing about it, maybe even gave yourself a little high five, only to stare at your screen 3 days later and completely forget what you did? Yeah, if you're nodding right now, trust me, we've all been there. It's so frustrating. It's a super common trap, right? Grinding away, peeking at the solutions, and trying to memorize every single step line by line. But spoiler alert, your brain is a terrible hard drive for raw, disconnected syntax. Think about that old, painful way of learning, brute force memorization. It makes your knowledge brittle. I mean, the second a problem changes, even slightly, you're stuck. But if we shift our mindset to building logical proofs, well, that changes the whole game. Algorithms aren't just static, boring sequences you cram the night before an interview. They're dynamic, problem-solving tools. And this is the absolute core of what we're talking about today. Logical proofs matter infinitely more than memorizing specific coding steps. Understand the proof, and suddenly, you're adaptable. You know, there's a saying I absolutely love. Algorithms were never created to be memorized. They were literally invented by people trying to solve very specific, really annoying problems. They were born out of pure logic and mathematical necessity. And once you truly grasp why an algorithm exists, like once you can actually prove its steps mathematically to yourself, remembering it becomes totally effortless. It just becomes common sense. You don't have to memorize that a stove is hot if you understand how fire works, right? Same exact thing here. So we're not starting with a fancy algorithm today. We're starting with a problem, and we're going to naturally discover the algorithm as the only logical conclusion. Okay, let's put this into practice with a beautifully simple problem. You've got an array of numbers, 2, 4, 6, 8, and 10. Your job? Find two numbers in this array that add up to exactly 10. That's the whole shebang. That's all the info you get, and that is your specific target. Target equals 10. Now, let's just take a brief second to really think about this. Don't guess, and please don't try to fish some fancy algorithm name out of your memory. Just use your own intuition. Looking at 2, 4, 6, 8, and 10, how would you find the pair that hits exactly 10? Just hold that initial approach in your head for a moment. Well, if your very first instinct was to check every single combination, that is exactly where your brain should go first. We could easily pair 2 with 4, then 2 with 6, 2 with 8, and so on. Then move on to the 4, pair it with 6, and keep going. Technically, this brute force method works. It's a valid solution. But wow, it is just way too much work. I mean, imagine if we had a million numbers instead of 5. That exhaustive pairing would take literally forever. So we need to ask ourselves a better question. Can we solve this exact same problem while doing significantly less work? To pull that off, we have to be really observant. What is the single, most critical piece of information hiding right in front of us? Look closely. The array is sorted. 2, 4, 6, 8, 10. Smallest to largest. This isn't just some random trivial detail. This is the entire key to unlocking a massive optimization. Because here is the thing. Great algorithms don't just invent new information out of thin air. They make better use of the information already available to us. This is a huge light bulb moment for anyone tackling data structures and algorithms. Making these small, really sharp observations about your data, like noticing it happens to be sorted, that is the actual foundation of logical proofs. We're going to leverage this sorted property to mathematically prove our way to the answer, totally bypassing all that tedious brute force checking we just talked about. All right, let's see how this logic actually builds. Imagine putting one pointer at our absolutely smallest number, the 2, and a second pointer at our absolutely largest number, the 10. I'm going to ask you a really fundamental question here. Knowing our target is exactly 10, can the number 10 ever actually be part of our final two-number answer? Think about it logically for a sec. Let's actually prove this with math. If we pair our largest number, 10, with our very smallest number, 2, what do we get? 2 plus 10 is 12, and 12 is already blowing past our target of 10. Because our array is sorted, we know for an absolute fact that every single other number, the 4, the 6, the 8, is strictly larger than 2. So 4 plus 10 is 14, 6 plus 10 is 16. The sums are only going to keep getting larger and larger. And boom, just like that, 10 is completely eliminated. It is mathematically impossible for 10 to be part of any pair that adds up to exactly 10 in this specific array. Notice what we did there. We didn't guess. We didn't write some exhaustive loop to check everything. We logically proved it, just by using the sorted property of the data. Any other pairing with that 10 is guaranteed to give us an even bigger, more impossible sum. And honestly, this right here is exactly why logical proofs matter infinitely more than memorizing steps. With that realization, we've unlocked the whole secret. Candidate eliminated equals move pointer. We just organically invented the famous two-pointer pattern. So when a tutorial tells you to move the right pointer to the left, it's not some arbitrary rule. Moving a pointer is just the physical manifestation of permanently tossing out an impossible option. You proved 10 can't work, so you toss it. You shift your right pointer inward to the next largest candidate, the 8. You see? You're not memorizing code. You're executing pure logical eliminations. Okay, let's play a little game and pressure test this new mental model. What if I completely scramble the array? Now we have 8, 2, 10, 4, and 6. Our target is still 10, but that absolutely crucial assumption we had, the sorted order, is totally gone. If we drop a pointer on the first number, 8, and the last number, 6, they add up to 14. Now, can we confidently say, oh, because this pair is too large, all other pairs with this number will definitely be too large? Can we logically eliminate the 6 or the 8 using that awesome, guaranteed elimination proof we just walked through? The answer is a hard no. Without that sorted order, our whole mathematical proof completely falls apart. Moving a pointer in a scrambled array doesn't guarantee you're moving to a definitively larger or smaller number. You lose the power to deduce anything. And this perfectly illustrates why the two-pointer pattern explicitly requires sorted data. It's not a rigid rule you just memorize, it's a fundamental logical dependency. So let's lock this core rule in. Sorted order allows us to permanently eliminate impossible candidates. Once you internalize that specific logical flow, I promise you, you will never, ever have to memorize the two-pointer pattern again. You'll just naturally reinvent it on the spot whenever you see a sorted array and a target sum. All right, I think you are totally ready for this. Let's immediately put your new proof-based mental model to the test with a fresh challenge. Here's a brand new sorted array, 1, 3, 5, 7, and 9. This time around, our target is exactly 8. So imagine your left pointer is sitting on the 1, and your right pointer is on the 9. Which pointer moves first? And more importantly, because we're relying entirely on logic and zero guessing, why? Try to justify it mathematically based on everything we just covered. I'll give you a couple of seconds to work it out. Look at the 1 and the 9, look at your target of 8, go ahead and prove the next move to yourself right now. All right, here is the reveal. 1 plus 9 equals 10. Our target is 8. Since 10 is greater than 8, and we're currently pairing the 9 with the absolute smallest number in the whole array, we can definitively prove that 9 cannot possibly pair with anything else to equal 8. Any other combo is just going to be bigger. Therefore, candidate 9 is logically eliminated. We discard it by moving that right pointer inward to the 7. See? You just executed the algorithm flawlessly, using nothing but pure logic. Seriously, step back and look at the amazing journey we just took. We went from simply noticing a sorted order to formulating a logical proof, which gave us the absolute confidence for candidate elimination, leading us directly to the two-pointer pattern. You didn't memorize a single line of code today. You deduced your way to a highly optimized algorithm. And because you proved it to yourself, it is going to stick in your brain way longer than any disconnected code snippet ever could. So this leaves us with one final kind of provocative question. Can this one simple logical deduction, based entirely on having sorted data, actually solve complex real-world interview problems? Well, the answer might surprise you, and it is exactly what we're going to unpack in the next explainer. Just remember, logical proofs always win out over memorizing steps. Keep thinking critically, keep proving your work, and I'll catch you next time.